Hello everyone, welcome back to Deterministic Optimization. We'll continue our discussion on algebraic aspects of linear optimization. In this lesson, we'll learn how to apply the concept of basic solution to standard form LP. Remember, standard form LP has the following form. So it's a minimization problem of minimizing C transpose X subject to a linear set of linear constraint AX equals B and X greater than or equal to 0. It's the non-negativity constraint on all variables. And here X is a n-dimensional variable, so X a vector with n components, and A is a m by n matrix, so that means AX equals B has m rows or m constraints, and of course because X is n-dimensional, so A has to have n columns. And remember, we assume that the m linear constraints in A or the m rows of A are linearly independent. If they are not, we can always remove the linear dependent ones because they can be expressed as a linear combination of other equality constraints, so they are redundant. Therefore, we can do some pre-processing if necessary to bring A to be a full rank matrix of rows. So in other words, we already have m linearly independent constraints in AX equals B. So what is basic solution in standard form? We already learned a basic solution is the unique solution to n linearly independent active constraints. N is the dimension of the variables. So that is a general property or general definition of basic solution. The question is how to apply this to standard form LP. So for standard form LP, we already have m linearly independent active constraints. Those are AX equals B. A has m rows, and they are linearly independent, and therefore they are linearly independent constraints. And it's equality constraint, AX equals B, so they are linearly independent active constraints. So we already have m. We need n, so we need an additional n minus m linearly independent active constraints. And where do we find them? Well, the only way to find them is from the non-negativity constraints, AX xi greater than or equal to 0, because that's the only set of constraints left there. And the question is which one of this n minus m additional non-negativity constraint come from? And here is the procedure to find a basic solution in standard form LP. We'll give the procedure first and then explain why it works. So since AX equals B has already m linearly independent rows, so there are also m linearly independent columns. This just comes from linear algebra. Therefore, we choose m linearly independent columns of A. And since A has m rows, if we choose m columns, then we have m by m submatrix of A, and we denote it as B. And this B matrix, because it has m rows, m columns, they are all linearly independent, this B matrix is actually invertible, and we call this B matrix basis matrix. And the corresponding xi's, meaning the xi's that correspond to the columns of B that we choose, are called basic variables. So they are denoted as a subvector xb, which is a subvector of the vector x. So in this way, A is partitioned as two submatrices, B and N. B is m columns, N has n minus m columns, because A in total has n columns. And the corresponding xi's of n, the columns of n, are called non-basic variables. So these basically xi's are the rest of the x outside of B. So we denote it as xn. And the way to find basic solution is to set all the variable xi to be 0 for xn. So in other words, for all these columns corresponding to n, I set the corresponding xi to be 0. I just zero out all of them. So in other words, these xi equal to 0 are active constraints coming from xi greater than or equal to 0. So the non-negativity constraint becomes active for how many of them? Well, n minus m, because there are n minus m non-basic variables. So why does this method work? So we can write, again, in a more compact form what we just did. We partitioned matrix A into B and N. B is n by m invertible matrix having m linearly independent columns, and then N collects all the rest of the n minus m columns. So correspondingly, we can partition X into XB, which is the variables corresponding to the columns of B, and also Xn, the non-basic variable corresponding to the columns of N. And we set Xn to be 0. So that's exactly the second constraint here. 0 and identity matrix times XB, Xn is exactly just Xn, and I set it to be 0. So this gives us n minus m active constraints coming from non-negativity constraints. And the top one, Bn times x, Bxn equals B, that just A times x equals B. So those are m linear independent constraints. So in total, we have n active constraints. Well, the question is, are these n active constraints also linearly independent? That is equivalent to say, if this matrix here, Bn and 0 identity, this matrix is invertible or not. Well, the one way to look at this and to view this actually is invertible is to view this matrix as a 2 by 2 matrix. So Bn, I, 0, these are all matrices, but we can view them as numbers. And these are 2 by 2 matrix. So the question is, well, we have an invertible matrix here and an identity matrix here. Is this matrix invertible? Yes, because you can see that the determinant of this matrix really determined by B and I. So, and both are invertible, so this whole matrix is invertible. So that means we have found n linearly independent active constraints. M of them comes from the equality Ax equals B, and n minus m of them comes from the non-negativity constraints. And the way to pick them is to first partition the matrix A into m columns that are linearly independent, and the rest that are either or not. We don't care if they are linear independent or not, but we set all the variables corresponding to those n minus m columns to be 0. Okay, and we can also write out what is xb and xn. Because xn is 0, so we can directly write here xn is 0. Then in the first equation, b times xb plus n times xn, xn is 0, equals b. So b times xb equals b. Therefore, xb is b inverse times b. Remember, b is chosen to be invertible. Okay, let's summarize what we learned. Well, we learned how to find n linearly independent active constraints in standard form problem. So this technique is really for finding a basic solution in standard form problem. And the key point here is to use the property that we can find m linearly independent columns from A. Thank you.